All right, so 2.88 says that there's a 25% chance that any CD is tested. All right, it's 1 out of every 4. Now the question says, part A says, what's the probability that a CD was tested and failed any test? Okay, any test. Okay, well that means it could have been tested and failed the first test, which was 0.01, or tested and failed the second test, which is, or tested and failed the third test, or tested and failed the excuse me, failed the fourth test. These are the only things that can happen. You couldn't have tested and passed. You would have either tested and then failed this test, or you tested and failed that test, or whatever. You didn't take 4 separate tests. You took one of those 4. That would be the answer for part A. For part B, it says, given that it was tested, what's the probability that it failed program 2 or 3? Okay. Well, this is the probability that it failed 2. This is the probability it failed 3. Okay. So given that it was tested, it's 0.25 is on the bottom. 0.25, 0.03. That is, it tested and failed. That one tested and failed. This one. Now you're like, but Jay, I feel like when you do this problem, you do the math on it here, and let me get a calculator here. Oh, here's one right here by me. 0.25. Oops, clear. 0.25 times 0.3. Oh, sorry, 0.03. Plus 0.25 times 0.02. So that numerator is 0.0125. Now, if you are a clever individual, you realize that that reduces. And so if you divide that by 0.25, you will find it is 0.05, which you could have done simply by doing this. Over here, there's a 5% chance. In other words, there's a 25% chance that you failed any one of these tests, right? So there's a 25% chance that you were tested, right? Now, of them, there's a 1 plus 3 is 4, plus 2 is 6, plus 1 is 7. 7% of the CDs, 7% of the tested CDs, if you will, failed the A test. 93% of them passed the test. Okay? The other 75% of all the tests together, of all the other CDs, were never tested at all. Okay? So it was either they weren't tested, that's 75% of them. The other 25 were tested, and then 5% of those failed, and then not 5%, 7% of those failed. The other 93% of those passed. Okay, so here's that case. Now, correct. All right, nice. Now, what about part C? Okay, so part C says, in a sample of 100, how many would you have expected to be rejected? It's a great question. So in a sample of 100 CDs, okay, well, we're going to test 25 of them in essence, correct? That makes sense? And we would expect exactly 7 of them to fail. Exactly what you had. Well done. Okay. Again, when you do the math on that, you bust all that out. That's the idea there. Let's see if we can prove that to ourselves there. So, yeah. So let's see this. If you bust that whole top line out, 0.25 times parentheses, that's 0.01 plus 0.03 plus 0.02 plus 0.01. Okay, it comes out to 0.0175. Now, you said it was 7%, right? 7 of them. Now, you got to be careful here. Okay, 7 is, you're saying that 7% of all of the CDs would be defective. Okay, that's what you're saying. That's hard to believe because only 1% fail this test. Only 3% fail this test, only 2% fail this test, only 1% fail this test. And yet, if I'm getting 7% to fail, at no point was I ever getting 7% failure rate. Does that make sense? In other words, I'm only going to get a few to fail this guy, a few to fail this guy, and so on and so forth. When you add this up, this comes out to be 0.0175, right? 0.0175, what does that mean? It means 1.75% of all CDs will test and fail. That makes sense? Well, 1.75 of what? Well, of 100. So I would expect 1.7 failures out of 100. That's what I would expect. Okay? So in other words, when you look at that 7% there, you were saying that 7% of the 25% would fail. And that's true. 7% of the 25%. But listen, we're talking out of all of them. Okay, out of all the CDs, how many would I reject? Well, 7% of 25%, which is 1.75%. So out of the 100 CDs, I would expect to fail about 1.75 of them for every 100. Oh, that's on average. Now, part D says, what's probability? Given the CD was defective. Ooh, what's the probability that it was tested? Ooh, interesting. Ouch. Okay. Now, pause for just a second there. Now, which I will say this though. Now, what you'll see here is this problem is kind of a Bayes theorem problem. Okay. Now, when we do this, one has to be a little bit careful because we don't know actual failure rates. Okay. We don't actually know. We don't know the actual failure rates here, so I got to think about this one for a second. Okay. Because there's some that are going to be there's some that are going to be defective that we're never going to test. So this is a Bayes theorem problem, and so here's the deal: they were either tested or not tested, right? And then of course you've got failure and not failure, failure and not failure. Okay. Or I'm sorry, defective and not. I'm sorry, defective and not. Let's write it right. Defective. Defective, not defective. Okay, so it says, given that it was defective, what's the probability that it was tested? Okay, well, there's defectives out here. So in other words, they could either be not tested and defective, or tested and defective over, and then of course we're interested in tested and defective. Okay, that's what we're looking for. So then this one on the top is obviously pretty straightforward. We know that it's 0.0175. Okay, that's what we know it is. Okay, now the bottom, of course, this one here is also the same. Now I'm going to stop and think for a jiffy on this other one. I think what they're going to have you do is do 0.75 times. I'm going to think about this for a minute. 0.01, 0.02 plus 0.02. Well, 0.07, right? The exact same failure rates as above. Okay? The exact same failure rates as above, because we're only testing a quarter of them. And so, yeah, that makes sense. So 0.0175 divided by 0.0175 plus 0.75 times 0.07. There's a 25% chance. The 25% chance that it was tested, given that it was defective. Now, does that make sense? Yes, yes, of course. Yes, of course, that makes perfect sense. Now think about that with me for a minute, okay? Because why? Because, and I apologize, I haven't done this problem in a few years. Every couple of years you get the same problems asked. This is one that's been a while. Think about this for a minute. So, in other words, they're either defective or they're not. Testing them has nothing to do with it. They have nothing to do with it. Testing has nothing to do with whether you're defective or not. It just shows that it was defective. It has nothing to do with it being defective. Okay, so I test 1 out of every 4 of them. There's basically a 7% chance. I mean, there was 1% here, 2%, 3%, 4%. Those guys all added together was 7%, right? So again, that was 0.0175 of all CDs were tested and defective. But this number here, which I didn't write down, let me write that down for you. 0.75 times 0.07, 0.0525. In other words, 5.25% of all CDs were not tested and yet will be defective. So that means there's a whopping grand total of about exactly 7%, I believe. Yeah, it's exactly 7%. Oops, 1.75% on top, 7% on the bottom. And that's 1/4 of all of the defective CDs will have been tested. Now, would I have done it that way? No, because if I was smart, I would have thought about it. I would have just gone, oh, well, duh. Okay, because they share the same. Whether I test you or not has no impact on whether you're defective or not. Okay, it just doesn't. This is not like, it's similar to, but it's different from in the Bayes theorem problem when we're drug testing you, because if you're on drugs, the test will behave differently on you versus if you're not on drugs. In this case here, these parts have already been made. We're just now testing them. You with me? And so the testing has nothing to do with it. All right, it's a random luck of the draw. You got chosen for the test, and we're going to find out if you're defective or not. So again, that's the game. Hope that makes sense.